if you've been following the conversation around AI, you know, the anxiety usually zeroes in on deepfakes or maybe massive job automation.
Right, or that far future kind of existential risk.
Exactly. But here's something that's maybe more interesting. What if the most immediate, the most concrete threat right now is actually a lot simpler? What if AI is about to become the world's best penetration tester?
The world's most effective hacker.
Yeah.
That is precisely the core concern. And the evidence, well, it shows it's really not theoretical anymore. Threat actors are already leveraging AI.
But to really get a handle on the risk, we need more than just, anecdotes. You need hard metrics.
On live systems,
And
that's the key.
okay, so let's unpack this. We've had attempts at benchmarking AI in security before, right? I mean, we've seen them pass capture the flag challenges, stuff like that.
Yeah, but those always felt like a sterile lab.
Totally clean.
Exactly. So the current benchmarks, Q&A formats or reproducing known vulnerabilities, they all have this critical gap. They miss the sheer scope, the noise, and the interactivity of a live enterprise network.
Because in the real world, breaches aren't usually from one perfect bug.
Never. They happen by chaining together messy misconfigurations, reusing old credentials, and just exploiting things across a huge, messy environment.
So what's our mission for you, the learner, today? This deep dive is based on a groundbreaking study that finally tackles that gap. It's the first comprehensive evaluation that puts AI agents head-to-head with human pros.
And not in a sandbox.
No, inside a real, live operational network. A massive university network, actually.
And the star of the show, so to speak, is a new AI agent framework called Artemis. It stands for Automated Red Teaming Engine with Multi-Agent Intelligence Supervision.
That's a mouthful.
It is, but it was specifically built to get past the limitations of older models like Todex or Cyagent. Their rigid structures, their inability to remember things over time. This was the real test.
Yeah.
Can AI truly compete with human expertise in a real-world pen test?
Okay, let's set the battlefield, because the researchers, they were meticulous about making this realistic. This wasn't just a handful of servers. Tell us about the scale here.
This test took place on a large research university's public and private computer science networks. The scale was substantial. We're talking about 8,000 distinct hosts.
8,000?
Yeah. Servers, workstations, IoT devices, all spread across 12 different subnets. And the environment was what we'd call highly heterogeneous.
Meaning it was a big mix of stuff.
A huge mix, not just Windows servers. You had Unix, embedded systems, all kinds of IoT things. And that variety, it exponentially increases the difficulty for any attacker, human or not.
And this wasn't some forgotten, unattached network either. It had real defenses.
Correct. They had baseline risk-based standards. So monthly vulnerability scanning with tools like Qualys, host-based firewalls, patch management. It was a tough nut to crack.
So on the human side, who were they up against?
They recruited 10 experienced cybersecurity professionals, real-world pen testers.
Okay.
And to keep things fair, they were all compensated $2,000 and standardized on a common platform, a Kali Linux virtual machine.
The gold standard for pen testers.
Exactly. It's loaded with all the tools you'd need.
I have to ask about safety. Live network, real pen testers.
Yeah.
How did they stop this from turning into a real disaster?
Right. Safeguards were absolutely paramount. The rules of engagement explicitly ban any destructive actions. No denial of service, no deleting data.
And someone was watching.
The university's IT staff had eyes on everything in real time. They were monitoring logs to make sure nobody, human or AI, went off the rails.
So, tough battlefield, seasoned players. Let's talk scoring. How did they decide who was winning? Because it's not just about counting bugs, is it?
Absolutely not. And this is where the study's design was really, really clever. The scoring framework they built was all about rewarding quality over quantity.
Technical sophistication and business impact.
Precisely. They used this metric, S-total, which combined technical complexity and weighted criticality.
And that technical complexity part.
Yeah.
What did that entail?
It's brilliant. You got a soft penalty if you only verified a vulnerability. Just pointing and saying, hey, there's a weakness there.
You had to actually exploit it.
You only got full credit if you successfully exploited it. That means you had to find the bug, chain the exploit, and actually compromise the system.
And the business impact weighting.
Yeah.
That makes it relevant to the C-suite.
Exactly. The weighting mirrored top-tier bug bounty programs. A critical vulnerability was worth 8 points, while a low-severity one was only worth 2. So the leaderboard wasn't going to be dominated by someone who just found 50 minor issues.
Okay, so Artemis was built to ace this very specific, very sophisticated test. You said older agents were brittle. Why did they have to build a whole new framework? Why not just plug, say, GPT-5 into an older one?
Well, the older architectures had a couple of fatal flaws for this kind of scenario. First, they're terrible at long horizon tasks. They get stuck in these short loops, constantly checking back with the user or just giving up.
And the second flaw.
Context fade, a huge problem. They couldn't manage the thousands of data points from a big network scan. They literally forget what they learned a few hours earlier.
So how does Artemis fix that? Let's get into the mechanics.
Okay, so Artemis is built around three core intelligence systems. First, you have the supervisor. Think of it as the project manager or the CEO. It manages the whole workflow, it holds the long-term memory, summarizes progress, and dictates the overall strategy.
So that solves the memory problem. What about speed?
That's where the swarm of arbitrary sub-agents comes in. The supervisor can spin up to 8 of these sub-agents to work in parallel.
Ah, so it's multitasking on a massive scale.
A massive scale. And each sub-agent gets custom instructions for its specific task. This is the key speed advantage. While a human is waiting for one long scan to finish, Artemis has already launched 7 other probes.
But if you're running all that in parallel, you must get a ton of noise. False alarms, right?
You would, and that's the job of the third piece. The triagger module. This is the quality control, the gatekeeper. It checks if a finding is relevant, it tries to reproduce the vulnerability to get solid evidence, and then it classifies the severity.
So it cuts down on the crying wolf problem that plagues older AI tools.
Massively. Which is what allows for that impressive longevity you mentioned. By breaking the work into sessions, summarizing progress, and then resuming, Artemis ran for 16 hours straight in the study. A human just can't maintain that level of focus.
And did the underlying model matter, like GPT-5 versus something else?
It did, but the architecture was the real game changer. So the A1 variant, using GPT-5, it outperformed half the humans. But if you put that same powerful GPT-5 model into an older scaffold like Codex, it performed way, way worse.
So it's not just the brain, it's the whole nervous system around it.
That's a perfect analogy. The Artemis architecture, its ability to manage complexity and parallelism, that's the real leap forward.
All right, let's get to the main event, the results. After those 10 hours of active engagement, where did Artemis end up on that leaderboard?
The bottom line was, well, it was genuinely provocative. The A2 configuration of Artemis, which used a more advanced model, placed second overall.
Second, out of 11 total participants.
Second overall. It outperformed 9 of the 10 seasoned human professionals.
Wow, that is a staggering result for a non-human agent in a messy real-world network.
It is. A2 found 9 valid vulnerabilities, and it had an 82% valid submission rate, which means very little noise. Now, to be clear, the humans as a group found way more, 49 unique vulnerabilities in total. So the agent didn't find the most, but it found some of the highest quality bugs, which the scoring system rewarded.
And you mentioned their approaches were different. How so?
The basic workflow was similar: scan, target, probe, exploit. But the top human performers balanced their automated scanning with really thorough manual validation. They would stop and think.
And the agent.
The agent had the built-in advantage of parallelism. We saw it happen. A single interesting signal would pop up, and Artemis would immediately launch multiple sub-agents to start probing different aspects of that target in the background.
So a human might see something interesting, make a note, and then get distracted and forget to come back to it.
We saw that exact thing happen. One participant, P2, noted a vulnerable server in their log but never went back to it. Probably fatigue or just shifting priorities. The agent doesn't get tired. It doesn't have shifting priorities. It just processes.
Okay, for you, the learner, this work is really practical. We have to talk money, the financial advantage.
Oh, absolutely. The cost difference is profound. So the A1 configuration, the GPT-5 one, cost $18.21 per hour to run.
$18 an hour.
If you annualize that for a standard work week, you're looking at an operational cost of about $37,000, $38,000.
So you have a hyper-competent pen tester, one that ranked in the top half of pros, for less than $40,000 a year. That just, it changes the economics of cybersecurity completely.
And even the more expensive A2 model, the one that came in second place, was still highly competitive. It cost $59 an hour, which is about $122,000 annualized.
And the average salary for a U.S. pen tester is?
It's over $125,000 a year. So Artemis, even in its best configuration, is already on par with, or cheaper than, a human professional.
So it's faster, works in parallel, costs less. Where did it fail? Where did the humans still have a clear advantage?
The biggest weakness by far was with GI tasks, anything requiring a graphical user
A
interface.
visual interface.
Right, so the researchers found this really critical remote code execution vulnerability on a Windows machine. You could only get to it through a web interface called TinyPilot. 80% of the humans found and exploited it. Artemis missed it completely.
Which makes sense. If you're built for the command line, a web page is like a brick wall.
It's a total blind spot. The human can see a button and click it. The AI, it struggles outside of text and structured data. It also made some more basic mistakes, like misinterpreting a 200 OK HTTP response as a successful login.
Why was that a mistake?
Because a human would see in their browser that the 200 OK was actually a redirect back to the login page.
Ah, so it was a failed attempt.
Exactly. The AI saw 200 OK, thought success, and moved on. The human realized they had been rejected. It's a subtle but critical difference in understanding context.
That said, being stuck on the command line wasn't all bad, was it? It actually gave it an edge at one point.
It really did, and this was one of the most surprising findings. So 60% of the human participants missed a vulnerability on an older IDRX server.
A remote management tool on a server.
Right. And the reason the humans missed it was because the server used an outdated HTTPS cipher. Modern browsers just refused to load the page, they saw an error and moved on.
But Artemis doesn't use a browser.
Exactly. It relies on command line tools like curl. And with a simple flag, decay, it told the tool to just ignore the certificate error and connect anyway. It successfully exploited the server. What was a roadblock for the humans was a non-issue for the AI.
So the humans were constrained by their convenient modern tools.
Yeah.
The AI just systematically pushed through.
It showed a kind of superior technical rigor in that one instance.
And did the researchers ever confirm that Artemis could have found the things it missed if it just got a little nudgy?
They did. They ran what they called elicitation trials. They gave the agent hints about 4 vulnerabilities it had missed, and with a medium or high hint, Artemis found all 4.
So the bottleneck isn't its ability to execute the hack.
No, it knows how to do in SQL injection. The bottleneck is in that higher level pattern recognition and planning, especially in a noisy environment. Its better context management actually meant it spent more time strategically thinking between submissions than the humans did.
So if we synthesize all of this, what's the one big takeaway you want our listener to walk away with?
I think the study provides really strong evidence that autonomous AI agents are not just viable for pen testing. They can perform at a technical level that is comparable to top professionals, and they do it because of their core strength. Systematic, fatigue-free work, great context management, and that game-changing ability to execute in parallel.
And the researchers are open sourcing the Artemis framework, which means defenders need to get their hands on this. If the attackers have it, the defenders need it more.
It's the dual-use reality. But here's the final provocative thought this whole study leaves us with.
Okay.
The humans and the AI agents, they were only allowed 10 hours of active engagement for this competition. But Artemis is designed for continuous long-term operation. So what happens? What kind of deep, devastating access does a scalable $18 an hour agent find when you give it not hours, but weeks to continuously and systematically work its way through a massive enterprise network?
That's the scale of the challenge we now face.